I deal with pain by tumor. Through tumor. We're turning it in. It's all everything in there? Yep. Let me know. I just looked it over. Yeah, you know, I just. Yeah.
Okay, those of you on Zoom, if you can hear me, give me a thumbs up or something like that. Okay, Amanda, you can hear me. Okay, good. Dane, can you hear me? And Meredith, you're in the last class, you can probably hear me. Okay. Great, thank you. Okay, those of you who have not taken the quiz, you can take it Monday. If that doesn't work, I'll email it to you, okay? I'll assume that's all right. Okay. All right, folks. Let's go ahead and get started. So, who can tell me some of the defining features of a competitive inhibitor? Looks like the transition state, okay? Binds to the active site. Does not change Vmax. Sorry? Oh, you might have that wrong. Well, Km stays the same. But sorry, Vmax stays the same. Km goes up. Km goes, it increases the Km. I think that's what you might have been getting at. Km goes up. Km goes up. All right, so competitive inhibitors bind the active site. They inhibit the active site. That's very important to remember. Uncompetitive inhibitors don't bind to the active site, they bind someplace else. They bind someplace else. And they bind only to the enzyme substrate complex. Only to the enzyme substrate complex. Yeah, yeah. So uncompetitive enzymes just bind the enzyme substrate complex. Competitive enzymes just bind the free enzyme.
What if they the enzyme binds to an inhibitor, just the enzyme, but it's not on the active site?
That's a different story, which we'll get to. That's mixed.
Okay.
That's mixed. All right, so the kinetics then for this, the reaction will look like this. You have an enzyme and substrate. That goes to enzyme substrate complex. But this inhibitor binds to that enzyme substrate complex. You don't get enzyme substrate complex. That must dissociate before this given that. You don't come up back to say some other stuff. That is the nature of uncompetitive inhibitor. An uncompetitive inhibitor. So, kinetically, what does this look like? If we take the Michaelis equation, we take this equation, now we're going to get a problem here. We're going to have an alpha is 1, plus the inhibitor concentration divided by K prime I. K prime I tells you it's not a competitive inhibitor, not a competitive inhibitor. Yeah. So the prime helps you designate between competitive and non-competitive. So Km goes down. So does the next. Km goes down. So does the next. Also, unlike competitive inhibitors, you can't swap out the inhibition of this enzyme with this inhibitor with more substrate. Can be done. So now your graph is going to look like this. So keeping the substrate the same here, and then gradually increasing inhibitor concentration to the double lanes. Notice the max with each one goes down, and Km also goes down. Next, inhibitors are mixed because they can do both. They can bind the free enzyme and to the enzyme substrate complex. That's why they're mixed.
I had a quick question.
Yeah, go ahead.
I know there's some inhibitors that when they bind to the enzyme, they don't bind at the active site. They bind at another site, but they change the conformation of an
Yeah,
enzyme.
that's allosteric. You're thinking of allosteric enzymes.
Okay.
That's regulatory. It's a regulatory step, and those enzymes depart from Michaelis-Menten kinetics.
Okay.
Savvy? Savvy? I guess so. All right. Next. These can do double duty. So they can bind the active site, but they can stick that bind someplace else too. So you've got this mess here. You have an enzyme and a substrate, and the free enzyme can be bound by the inhibitor, and you have the enzyme inhibitor complex. Now, this is associated. So by this, both cases, you still need the inhibitor to substrate before you make product. These tend to be the most potent of the non-reversible inhibitors. These tend to be the most potent. That's the most inhibitory worlds. Inhibitory back to back. Now the kinetics get messy. So you have an alpha and an alpha over here. And typically alpha and alpha numbers are different because the inhibitor has two very different affinities for the active site and the other inhibitory site. So alpha is 1 over inhibitor divided by case of I, that's its affinity for the active site. I, one plus inhibitor by K, when I has its affinity for the other site. And there are some inhibitors that actually bind multiple sites. Wow, and it really messed up. So these affect both Kmax and Km. Now, Km may go down, it may go up, depends on the inhibitor. So you use inhibitors will usually look something like this when you do a graph. Up and it does. Sometimes it goes up, depends. So, saccharin is red, black pepper. And saccharin is a mixed inhibitor of the human drug transport animal gene. It also is a mixed inhibitor of the drug metabolizing enzyme in your liver, cytochrome B4, which is one of the major drug metabolizing enzymes. Now, unfortunately, there's not very much in pepper, and you don't use very much pepper on your food to cause like problems unless you're very understanding who practically takes a little food. But most reasonable people aren't going to have a problem with pepper and their drinks. To prevent you from processing the drug, so the half-life of the drug goes way up. And you start to get side effects. As the drug acute, as the drug will accumulate now in your blood. So, drugs, as we create for are steps. And this concentration goes up, and it's going to damage your muscles. You're going to start to get cramp, all this. And that can destroy muscle, but also destroy tubes. So, just a little bit of a food go down. Nice. Crackling noise. Crackling noise. Can you hear me now? Dan is shaking his head. Let me, oh boy.
Do
Okay.
you have like your headset microphone? Because it really happens like the worst when you start moving around. But like if you're just standing here talking to us, it starts to go away.
Let me, I have to stop sharing. Let me test my microphone.
Yeah, like it's perfect right now.
Okay. How about now? Can you hear me now?
Yeah, you're good now.
Okay. Yes. 7 years ago, blah, 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 blah. In the beginning was the Word, and the Word was with God. Yeah, okay, that's fine. So,
Cool.
all right, and let's keep going. Okay. All right, now so pepper, yeah, is a mixed inhibitor. Now, if you are a mixed inhibitor, and your alpha equals alpha prime. Then you are a non-competitive inhibitor. So it's a subcategory of mixed inhibitors. Subcategory of mixed inhibitors. And in this case, you will have a decrease in Vmax, but Km will stay the same. Vmax goes down. Km stays the same. Yep, that's exactly what it means. And here is a graph of a non-competitive inhibitor. Pretty hard to miss, but this is not very common. However, I will say lead is a non-competitive inhibitor of two enzymes involved in the synthesis of heme. So you do see this clinically. So uncompetitive and mixed competitive inhibition are seen typically in enzymes with more than one substrate, usually. And inhibition studies can tell you a lot about the kinetics of the enzyme. So they're very important for enzymatic studies. If you're studying an enzyme, you're going to do inhibition studies. There's just no two ways about it. So this is your rules from the book. And if the substrate and the inhibitor are mutually exclusive, you have yourself a competitive inhibitor. If I and S are not mutually exclusive, not mutually exclusive, and both ligands bind independently of each other, then you might very well have a non-competitive inhibitor. Non-competitive inhibitor. Rule number 3, if the inhibitor affects the affinity of the enzyme for the substrate, it's usually a mixed inhibitor. If the inhibitor affects the affinity of the enzyme for the substrate, it's probably a mixed inhibitor. And then if the inhibitor binds after S is bound, it's an uncompetitive inhibitor. If it binds after S is bound, it's an uncompetitive inhibitor. And this table here from your book shows you the effects of these inhibitors on enzymes. And yeah, I quite like this table, frankly. The gap goes down, goes over. Okay. Questions about inhibitors, anyone? So enzymes have a sweet spot where they work. That sweet spot will allow them to do their catalyzing of reactions with a great deal of efficiency. Some enzymes have very wide conditions under which they're effective. Others don't. Depends on the enzyme. So pH and temperature are the two biggies, but so is osmotic pressure So is ionic concentration. So is atmospheric pressure. All of these can affect the activity of enzymes. So pepsin is quite active at pH 2. After that, its activity hits the skids. But glucose 6 phosphatase, that's most active around neutral pHs. Between those, it's not so active. Different enzymes have different optima. Most of the enzymes in our bodies work in that neutral optima. Hence the buffers in your blood that keep it within those those sets of optima. Same thing with temperature. Most of our enzymes work at 37. You start getting outside 37, they may not work as well. So many of our enzymes are narrow in their optima. Not all, but many are.
So you mentioned atmospheric pressure. So like if you go like climbing like on mountains, does that affect enzymes a lot or no, or is it not affected?
Oh, it affects saturation of blood with O2, yeah. But it is going to mess with your enzymes terribly. Oh, not really. Not really.
A little, but that's not like the thing to be worried about.
Yeah. That's the least of your worries. Now, this gets to what Amanda was asking about earlier. So with your biochemical pathways that make things. So you start here, you go to here, and each one is an enzyme catalyzed step. That makes a series of intermediates. These types of enzymes in such pathways are heavily regulated, very heavily regulated. Now, these enzymes will obey Michaelis-Menten kinetics, but their regulation often causes them to depart from Michaelis-Menten kinetics. And these are regulatory enzymes. And they depart from Michaelis-Menten kinetics. And I'll show you when they do, because that's important. So first, these regulatory enzymes are sometimes covalently modified. That can either activate them or it can inhibit them. So that covalent modification can often affect the way they engage with their substrate, and it can also cause them to depart from Michaelis-Menten kinetics. Instead of a regular hyperbolic curve, you make it a sigmoid curve, so that the enzyme only works now at very high substrate concentrations. That's one type of modification you may see. There's also a group of regulatory enzymes called allosteric enzymes. They have sites other than the active site, usually. And if they're bound by small molecules, things called allosteric modulators. These modulators will affect their ability either positively or negatively. It depends. And they bind usually a site other than the active site. When they do, they tend to depart from Michaelis-Menten kinetics. And this type of regulation is way common. Way common. Now, allosteric enzymes can either change their conformation when they're bound by allosteric modulators. Sometimes these things are bound by more than one allosteric modulator. And it takes a combined effort from different modulators to get the enzyme to do this thing or that thing or whatever. Now, there's a group of allosteric enzymes called homotropic enzymes. Homotropic. These enzymes, homotropic enzymes, they actually have a special active site, and the active site is both the active site and the regulatory site. If the, yeah, I just said that, okay. If the regulatory site and the active site are distinct, then you have a heterotropic enzyme. Heterotropic enzyme. And these are more common. These are definitely more common.
So for the other one, you have two different molecules binding to the same site.
Yeah.
Okay.
Freaky, huh? The kinetics, the way the kinetics are affected differs from enzyme to enzyme. So you may have something that looks I'm gonna draw something on the board, guys, see if you can see this. You may get something like this. And then if bound by the effector, you may get something like this. That looks almost linear, doesn't it? Or something like this, where higher substrates actually start to inhibit the enzyme. So it can vary. The types of kinetic variations will vary. That's the piece I'm trying to get you to see here. Okay. Feedback inhibition is a common application of allosteric enzymes. And this is used to control biosynthetic pathways. So you're not making things you don't need. This prevents the buildup of molecules and the waste of energy into making things you just don't need. So let's take, for example, isoleucine. Isoleucine is made from the amino acid threonine. And the very first enzyme involved in threonine synthesis is threonine dehydratase. Threonine dehydratase. That produces alpha ketobutyrate. And then alpha ketobutyrate is a substrate for another enzyme, acetohydroxy acid synthase. And then there's another one that works on another. I just don't want to read you the riot act on that. Just this is the first step in the synthesis of isoleucine. So if isoleucine builds up in concentration, you have more isoleucine than you need. Isoleucine will feed back, inhibit threonine dehydratase. Oh, too much isoleucine will inhibit the first enzyme in that pathway. That way, you don't waste energy making isoleucine, because isoleucine is energetically expensive to make. This clear? This is very common. Very, very common. Those of you who stick with me next semester and you have to deal with all those pathways, you're going to see this coming out of your ears. You're going to see this all the time because that's really common. Now, why don't you inhibit this enzyme? Why the first one? Say it again, Greg? Yeah, yeah, exactly. These steps take energy. So this shuts it down so you're not wasting resources making these intermediates. Very good, exactly right. Okay. And this inhibition is concentration dependent. And when it binds, this enzyme departs from Michaelis-Menten kinetics. And you can see this here, there's a picture shamelessly stolen from your book. Your book talks about these things called did you read about those yet? So some enzymes are made as precursors that have to be clipped before they're active. A lot of your digestive enzymes are this way. These inactive precursors are called zymogens. Zymogens.
So, quick question.
Go ahead.
So like the amino acids and stuff like that that are present within supplements. So I know that when you take like too much of like vitamin B or something, you just dispose of it as a waste product. Is that the
Yeah.
same thing with amino acids?
Yeah.
Okay.
That was your question?
Yeah,
Oh, okay.
sorry.
No, that's okay. All right. Any questions here? Okay. Let's now look at, oh dear. There, okay. All righty. All right, let's go to carbohydrates. All righty. Carbohydrates are very abundant. Easily, they're the most abundant of the biochemical molecules on the face of the earth. Very, very, very abundant. They are used for storage of energy, starch, glycogen, things like that. They are very readily utilized to make energy, and they can also provide structural elements that are unique. So they're everywhere. They're very abundant. So the simplest of the carbohydrates, of course, are the monosaccharides. Carbs are very, very polar. They're very soluble in water, consequently. So when Jessica had to make the 25% glucose solution, she probably noticed it went into solution pretty easily, even though it was 25 grams per 100 mils. That is a testimony to how polar these compounds are. They have between 3 and 7 carbons. 3 and 7 carbons. You have less or more, you're not a carbohydrate. You might be a carbohydrate derivatives, but you're not a carbohydrate. You're not a simple carbohydrate.
Your slides aren't changing for us.
Let's try
Sorry.
again. That better? Good.
If you're switching between slides, I mean, it's on the right slide now, but if you're trying to change between them, it's still not changing.
Yeah. How's that?
There we go.
Okay.
Thank you.
Okay. Carbs are chiral. They're chiral. They have stereoisomers. This is quite important too, because living organisms use one stereoisomer over the other. So that's important too. So these monosaccharides can end in a aldehyde, or they can end in an alcohol and have a ketone. If they have a ketone, they are ketose sugars. Ketose sugars. If they end in an aldehyde, they are aldose sugars. Aldose sugars. So the 3-carbon sugar is a triose. 4-carbon sugar is a tetrose. 5-carbon sugar is a, well, it's right up there on the board, pentose. 6-carbon sugar is a hexose. 7-carbon sugar is a heptose. Can you have an 8-carbon sugar? No. So this is what you have. And if you have a triose, that's a aldose. You have a aldotriose. If you have a pentose, that's an aldose. You have a aldopentose. If you have a 6-carbon sugar, that's a ketose. It's a ketohexose, and so on and so forth. That's how you describe monosaccharides. So here is glucose. It is a aldohexose. 1, 2, 3, 4, 5, 6. Fructose is a ketohexose. Ketohexose. Now, the stereochemistry of these things is a little bit weird. What you do is you take the atom of the molecule and you compare it to glyceraldehyde. If it looks like D glyceraldehyde, it's a D sugar. If it looks like L glyceraldehyde, it's an L sugar. This is your standard of comparison. So you don't take some particular carbon. No, you compare it to these two standards. And if it's like this, it's D. If it's like this, it's L.
Hydroxide group do you compare to?
The bottom one. So the this here. Yeah, that one there. So it's D because that's over here. So let's go back, toggle back. You can see there, that one, let me, let's see. Well, let me do it. This one here, it's on this side, so that's D. This one here is on this side, that's D. If it was over here, then it'd be L. And in living systems, D sugars are usually what you see. Not L, but D. You have L amino acids, D sugars. There is one compound that's not chiral, and that's dihydroxyacetone. And dihydroxyacetone can that be chiral? In the end, it's symmetrical. There's no asymmetry. You have to have asymmetry for chirality, right? So that's the only one that's not chiral. All your other sugars are chiral. Now, when you look at sugars, they can differ around only one carbon. So let's take a look at a few examples. Last, I don't have pictures of them. There. So here's glucose, here's mannose, okay? Same, 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 not same, same. They differ around one carbon. They're called epimers. Epimers. So mannose is a C2 epimer of glucose. C2 epimer of glucose. What about galactose? Same, same, not same. Same, same, same. Galactose is a C4 epimer of glucose. C4. No, then it's not an epimer. Yeah, by definition, epimers differ around one carbon and one carbon only. Yeah, so said that. Okay, good. Okay. Now, a question I always get, and it's a fair question, is how many of these do I have to know structurally? And here's my rule. If there's a box around it, you have to know the structure. Because those are the most common. So here's the aldoses. Glyceraldehyde, there's just one. 4 carbons. There is erythros and threose. Erythros and threose. You need to know only the structure of erythros. Here are the aldopentoses. Ribose, arabinose, xylose, lysose. You need to know only these. And looky here, gang. Same, no. Arabinose is a C2 epimer of ribose. Xylose is a C3 epimer of ribose. You remember that? You remember the structures.
When you say epimer of, how do you know which one to compare to?
Because ribose is really easy. See how easy ribose is? So compared to ribose, you'll never go wrong. Yeah. Sure, I could, but I didn't. Because I'm going to bet you. I'll bet you a Kit Kat that you'll know how to draw this before you'll know how to draw this. So use that, and memorizing the structure will be easy. No, it's not. Of ribose, no. But it is an epimer of xylose.
But it is true that we could say ribose is.
Oh yeah, you could. You could. And usually the most abundant sugar is the one you're going to use. And out of these, ribose is definitely the most abundant, by far. Now come the aldohexoses. Aldohexoses. So the granddaddy of this group, of course, is glucose. Glucose. So you need to know glucose, mannose, and galactose. glucose, mannose, and galactose. The others are not very common at all. Now we come to the ketoses. There are no C4 ketoses. There are, however, C5 ketoses. So you have a keto pentose, you have ribulose and xylulose. Ribulose and xylulose. 6 carbon ketoses, ketohexoses. You have fructose. The others are not at all common. Sucrose, sorbose, targetose, not common at all. You don't need to know those.
So we should be memorizing the Fisher projection of these, correct?
For now, yeah.
Okay.
Notice this convention. Ribose is a aldose. Ribulose is a ketose. Xylose is a aldose. Xylulose is a ketose. That's a common thread in the nomenclature. Now, these Fisher projections, that's what they look like in crystals. So the glucose that you get upstairs, it's crystalline. It looks like that. But when you put it in water, it cyclizes. The cyclic form is much more stable in water. So that's the predominant form in water. This is an intramolecular reaction. And if you are an aldehyde, you'll make the acetal. If you're a ketone, you'll make the ketal, well, hemiacetal, acetal. You'll have usually the hemiacetal. Then you have the hemiketal. And let's see how this works. So here's D-glucose. You'll have a reaction between the aldehyde and this alcohol here. Aldehydes are reactive, right? Aldehydes are reactive, right? Thank you. I don't have to go to Dr. Baldwin crying now. So the reaction will generate this ring structure. This is called a pyranose ring. Pyranose ring, and it goes carbon 1, 2, 3, 4, 5, 6. Carbon 1, 2, 3, 4, 5, 6. The oxygen is part of the ring. This is not a planar structure, not by a long shot. And there are two forms. There's an alpha and a beta form. An alpha and a beta form. We'll get into the geometry of this when we come back on Monday. Very good. Have a great weekend. See you guys. And be ready to do chicken gizzards on Tuesday. Kitty! Oh, kitty! That's a big kitty.
Yeah, he's very fat. He's a food boy.
Kitty!
Have a good weekend.